Fluids at rest. Fluids and the world around us. Fluids, which includes both liquids and gases, play a central role in our daily lives. We breathe and drink them, and rather vital fluid circulates in the human's cardiovascular system. There's the fluid ocean and the fluid atmosphere. What is a fluid? A fluid, in contrast to a solid, is a substance that can flow. Fluids can form the boundaries of any container in which we put them. They do so because a fluid cannot sustain a force that is tangential to its surface. In a more formal language, a fluid is a substance that flows because it cannot withstand a shearing stress. It can, however, exert a force in a direction perpendicular to its surface. In fluids, there's no orderly long-range arrangement of constituent atoms. Density and pressure. With fluids, we are more interested in properties that vary from point to point in an extended substance than with properties of specific lumps of that substances. It is more useful to speak of density and the pressure than of mass and force. Density, rho, equals delta m over delta v. The unit is kilogram cube a meter. In theory, the density at any point in fluid is the limit of this ratio, as the volume element delta V at that point is made smaller and smaller. In practice, we assume that a fluid sample is large compared to atomic dimensions and thus smooth with uniform density rather than lumpy with atoms. These assumptions allows us to write above equation the form rho equals m over v, not delta m delta v, where m and v are the mass and the volume of the sample. Note that the density of a gas varies considerably with pressure, but the density of a liquid does not. That is, gases are readily compressible, but the liquids are not.
Air is compressible. If we fill the syringe with air and place it between two wooden blocks, a weight placed on the upper block can easily compress the air. Water is not as compressible. If the syringe is filled with water instead of air, and the demonstration is repeated, even large amounts of weight do not compress the water significantly.
Pressure. P equals delta F over delta A. The unit is Pascal. 1 Pascal equals 1 Newton over square meter. We have a sensor for this one. We can apply the area as delta A, the force delta F, and we get the pressure. In theory, the pressure at any point in the fluid is the limit of this ratio, as the area dA of the piston center on that point is made smaller and smaller. However, if the force is uniform over a flat area A, we can write P delta F over delta A as P equals F over A. When we say a force is uniform over an area, we mean that the same force would be measured at every point of the area. We found by experiment that At a given point in a fluid at rest, the pressure P, defined by P equals F over A, has the same value no matter how the pressure sensor is oriented. So the pressure is a scalar, having no directionality properties. The Pascal is related to some other common non-metric system pressure units as follows. 1 atmosphere equal to 1.1 times 10 to the 5th Pascal is around 760 torr. The atmosphere is, the name suggests, the approximate average pressure of the atmosphere at sea level. This one, atmosphere. The torr, named by Torricelli, who invented the mercury barometer in 1674, was formerly called the millimeter of mercury. Millimeter of mercury.
We'll use this water manometer driven by a flexible rubber diaphragm to show that pressure in a fluid is independent of direction. When the diaphragm is lowered into a jar of water, the manometer indicates the pressure increase with depth. When the diaphragm is held at a constant depth and turned to different directions, the reading on the manometer stays constant. The pressure in the water is the same in all directions.
This is some pressure where it goes through. The best laboratory vacuum is 10 to the minus 12. That's very low, very low. That's a vacuum, okay? The center of sound, you have a pressure 10 to the 16. Huge pressure.
We'll use these two small hemispheres to demonstrate the force due to air pressure. If the hemispheres are placed together with air inside, pressure is the same inside and outside, and the hemispheres are easily separated. But if we remove the air from the inside with a vacuum pump, the air pressure on the outside is no longer balanced by pressure on the inside. The hemispheres will support a large weight without separating. When air is allowed back in, the hemispheres fall apart. This animation shows the forces due to air molecules striking the inner and outer surfaces. Normally they balance, but when the air is removed, the force on the inner walls vanishes. The unbalanced force on the outer walls must be overcome to separate the hemispheres.
These thick glass plates have surfaces that are microscopically flat. When they are pushed together, the air between the two faces is squeezed out. The atmospheric pressure outside the plates now holds them together. We'll use the power of atmospheric pressure to launch a rubber ball at high speed. The rubber ball is put inside this long tube, and both ends of the tube are sealed with metal plates. A vacuum pump attached to the tube then removes the air from the tube. When the tube is completely evacuated, the metal plate nearest the rubber ball is knocked off. The rush of air into the tube blows the rubber ball out the other end of the tube at high speed. This thin rubber sheet will be used to demonstrate the large forces produced by air pressure. When the sheet is placed on top of this stool, the air between the sheet and the stool is driven out. The air pressure on the top of the sheet holds the sheet to the stool with enough force to allow the stool to be lifted off the ground with the sheet.
Fluid at rest. We look at this cuboid, okay, with its cross areas A, okay, this is length, okay. Okay, look at one surface at the level y1. This one is level y2. This pressure we call it P1. This level pressure is P2. Okay, and then we look at this. What is physics? First, this cuboid is at rest. That means the total sigma force equal to 0, right? Yeah. Then second, how many forces vertically they have? The first one is the gravitational force mg. Another one is the force from the fluid on top floor, those the F1, and the F1 is going down. Another pressure is from liquid, it's called F2. Okay, so we have it is at rest, it is at equilibrium, the sigma F equal to 0 vertically. So we have F2 equal to F1 plus mg. What is F2? F2 is equal to the pressure times the area. F1 is pressure times area, right? Yeah. These two pressure are different because the different depths, okay? And then M, this mass of this cuboid is equal to rho times V. Rho is the density of water. The V is equal to area multiplied by the height. The height is y1 over y2, okay? Because we take the y's upward as a positive direction. So in this case, y1 is larger than y2. So this is a positive number, okay? And we put all these black, this white, and the blue inside. We get F2 M P2A equal to F1 P1A equal to mg m, which is rho A y1 minus 2 g. So this equation we cancel out A. Okay, we get P2 equal to P1 plus rho g y1 minus y2. Let me a little bit change this one. Suppose y1, this cuboid is on the top. y1 is 0, okay, and y2 is minus h. So in this one, P1 is the P0. Whether P0 is the atmosphere pressure on the surface. Okay? So we put those inside. Okay, we get P at this point, P2, P equal to what? P equal to P0 plus rho GH. This is the fluid at rest. That means the pressure at deep point H, okay, equal to P0 plus rho GH. Pressure at depth H. We see this is references at the surface of the liquid, y equal to 0. And this is a P0 is atmosphere pressure. And this is a point P in the deep H in the water or in the liquid. Okay. We see the pressure P equals P0 plus rho GH. The pressure at a point in the fluid in a static equilibrium depends on the depth of that point, but not on any horizontal dimension of the fluid or its container. Thus, above equation holds no matter what the shape of the container is. In the above equation, the pressure P is said to be the total pressure or absolute pressure. The difference between an absolute pressure and an atmosphere pressure is called the gauge pressure. The name comes from the use of a gauge to measure this difference in pressure.
This is an electronic pressure gauge which has a pressure sensor at the bottom. Blowing into the sensor through a tube increases the pressure and drives a bar graph display whose length is proportional to the pressure at the sensor. When the pressure gauge is placed in a column of water, the display shows that the pressure increases in direct proportion to the depth of the sensor. If we replace the water in the column with alcohol, which has a lower density than water, how will the pressure readings be affected? The reading is lower in alcohol than at the same depth in water, but it is still proportional to the depth.
The mercury in this U-shaped tube is in equilibrium when the surface of the mercury is at the same height in both sides of the tube. But when colored water is added to one side, the fluids come to equilibrium with their surfaces at different heights. The pressure at the bottom of each leg must still be the same, but the amount of fluid required to produce that pressure is different on each side.
Sample. A novice scuba diver practicing in a swimming pool takes enough air from his tank to full expand his lungs before abandoning the tank at the depth air and swimming to the surface. He ignores his instructions and fails to exhale during his ascent. When he reaches the surface, the pressure difference between the external pressure on him and the air in his lungs is 70 torr. From what depth did he start? What potentially lethal dangers does he face? We look at this equation, okay, we see the P minus P0 is 70 torr. Delta P is equal to rho GL. And this number is given 70 torr. Okay, so we can find the air. Right? Remember that one. This one should be used to Pascal. And this is the torr. Okay, so we have to 706 torr is 1 atmosphere, 1.11060. So this is 9,300 Pascal. We put this inside, we get air. This rho is the density of water, 998. This is the gravitational acceleration, 9.8. So the depth is 0.95 meter. It's only 1 meter, it's not 5. But this is not deep, yet the pressure difference of 9.3 kilopascal, about 9% of atmospheric pressure, is sufficient to rupture the diver's lungs and force air from them into the depressurized blood, which then carries the air to the heart, killing the diver. If the diver follows instructions and gradually exhales as he ascends, he allows the pressure in his lungs to equalize with the external pressure, and then there's no danger. Example, the U-tube in the figure contains two liquids, okay, in a static equilibrium. Water of the density rho W, okay, in the right arm, and oil of unknown density rho X in the left. Measurement gives L equals 135 millimeter and D 12.3 millimeter. What is the density of the oil? Let's look at this one. The physics here is interface, okay? We see on the interface, the left side and the right side, their pressure should be the same. This is the physics, okay? So let us see what is the interface pressure, okay? Let's see, on the right side, this is water equal to rho GL, P0 per rho GL. And here is P0 plus rho X G L plus D. So from this equation, we cancel out the P0, we get a rho X. Okay, we put a number inside, and we get this about 915 kilogram per cubic meter. This equation, nothing to do with G and nothing to do with P0. Measuring closure. The mercury barometer, this is mercury, this is vacuum, P equals 0. This is air, the pressure is air pressure, atmosphere. Whatever the shape it is, we see this is the same, H, K, this is the same. It's nothing to do the shape or the horizontal situation. Then we see P2, okay? P2 equals P1, okay, plus Y1. What is 1? And this is a 1, this is a 2, okay? So the pressure here equal to P1 plus rho G Y1 minus Y2, okay? This is Y1, we take it as 0, reference here, okay? And we see Y2 is H, all right? Y2 is H. And we see P1 is P0, the atmosphere, and P2 is 0 because it's vacuum. We put this one inside this equation, we get P0 equal to rho GH. So from this H, from the density of this mercury, we can measure the P0, that means the atmosphere, okay? This is called millimeter mercury, or torr. The column height in millimeters is numerically equal to the pressure in torr, only if the barometer is a place where G has an accepted standard value of 9.80665 meter per square second, and the temperature of the mercury is 0 degree. Only in this situation, this is equal to this one, okay? The open tube manometer, this is the open. This is the pressure we're going to measure. We will see this one, this is H, and we find P2 here equal to P1 times Y1 minus Y2, right? This is H, okay? With Y1, we call it 0. Y2 is minus H, okay? So this is H, okay, we get it. P1 is here, is equal to this open tube. So this is equal to atmosphere pressure, okay? And then P2 is the pressure here, is the pressure we're going to measure, okay? So this is the gauge pressure, okay? PG at this point is P2. Is P2 is P minus P0. This is the pressure P. This is P0 time. And this one, rho GH, remind this one, we have the gauge pressure, not absolute pressure, okay? It's minus atmosphere pressure. An open tube manometer measures the gauge pressure Pg of a gas, which is its real pressure minus the atmosphere pressure.